Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module PN junction diode, characteristics of solar cell from the paper Energy related materials. So the main points which will be covered in this module are: first, we will be discussing what is a PN junction diode. Second, the behavior of PN junction under dark and illuminated situation. Third, the physical significance of short circuit current, open circuit voltage, and the fill factor. Lastly, we will be discussing the series and the shunt resistance. So students, let us start with a brief introduction about the module. The planar PN junction solar cell under low injection is usually singled out for special analysis since realistic approximations exist that allows analytic solutions to be developed and used successfully for the description of practical devices. The success of this model is due to a large extent to the clear way the cell can be divided into three regions: emitter, junction region, and base, that serve a different purpose in solar cell operation. The emitter and the base, which remain largely neutral during the cell operation, absorb the main part of the incident light and transport the photo-generated minority carriers to the junction. The PN junction, which contains a strong electric field and a fixed space charge, separates the minority carriers that are collected from the emitter and the base. The junction is effectively devoid of mobile charge carriers and is sometimes called as the depletion region. PN junction. So students, as we know that the PN junction is an important part to study the characteristics of the solar cell. So let us discuss about the PN junction diode. When a semiconductor is doped with a pentavalent or donor impurity, it is known as N-type semiconductor, and if it is doped with trivalent or an acceptor impurity, it is known as P-type semiconductor. The energy versus distance diagram for the intrinsic N-type and P-type semiconductors with the positions of the Fermi level is shown in the figure. In this section, the basic properties of PN junction diode will be analyzed under both illumination and dark conditions. The basic device requirements for solar energy conversion to electricity is an electronic asymmetry in the semiconductor structure, which is shown in the figure. This shows that a PN junction diode has that required asymmetry. Generally, the N-type semiconductors have large electron density but small hole densities, whereas P-type semiconductors have large hole densities and small electron densities. Hence, electron in the N-type semiconductor and holes in P-type semiconductor can flow readily, but holes in the N-type and electrons in the P-type find it very difficult. When a PN junction is illuminated, the excess electron-hole pairs are generated by the light in the semiconductor. The inherent asymmetry of the PN junction diode encourages the flow of generated electrons from P-type region to the N-type region, and the flow of holes in the opposite direction. So a short circuit current flows in the circuit when this illuminated PN junction diode is electrically shorted. The biasing of PN junction diode and its characteristics. The most common solar cell is nothing but just a large area PN junction diode. The PN junction diodes are formed by combining P-type and N-type semiconductor. Now let us consider the isolated blocks of N-type and P-type semiconductors as shown in the figure A. Conceptually, if these two blocks are brought close to each other, then it would be expected that electrons would flow towards the lower concentration region, that is P-type side, from higher concentration region, that is N-type side, and holes from P-type side to N-type side. The electrons flowing towards the P-type side will create a charge imbalance in the N-type side by exposing a positive charge or ionized donor. Similarly, holes flowing towards N-type side will expose P-type side by the negative charge or acceptor ions. These exposed charges will form an electrical potential which will oppose the natural migration of electrons and holes and result in an equilibrium situation. The characteristics of equilibrium situation can be described by considering the Fermi level. A PN junction device in thermal equilibrium has only one Fermi level, which is shown in the figure, that there is only one Fermi level, and due to the alignment of the Fermi level, the bands, that is energy bands towards P-type side, bend downwards as compared to the energy bands towards the N-type side. So this band bending occurs in the depletion or the transition region. Now let us consider that a voltage is applied across this PN junction in such a way that the P side is connected to the positive terminal and N side is connected to the negative terminal. This configuration is called as forward bias PN junction, which is shown in figure C. In this case, the holes and the electrons, they are repelled from the positive and the negative terminals of the battery and are forced to move towards the junction. Hence, the internal energy barriers will be reduced and the electrons can easily enter the P material and holes into the N material. As there are sufficient electrons in the N region and holes in the P region, they are available to cross the barrier, hence the current flow increases sharply. Now let us consider another configuration where the P side is connected to the negative terminal and N side to the positive terminal as shown in figure D. This configuration is known as reverse bias PN junction. In such configuration, the holes in the P region, they are attracted towards the negative terminal and electrons in the N region are attracted towards the positive terminal of the battery. Therefore, the majority carriers are drawn away from the PN junction, which results in a wider depletion region and hence increases the potential barrier. Further, the majority carriers cannot cross the junction due to increased potential barrier, resulting in no flow of current. However, small current which will flow through the PN junction will be due to the minority carriers, that is, due to the flow of electrons from the P region and holes from the N region. Now let us discuss the characteristics of solar cell. This graph shows the current versus voltage characteristics of the solar cell when it is dark, that is A graph, and the B graph shows the characteristics of the solar cell when it is illuminated. And there are two parameters which have been shown on the graph, that is VOC, open circuit voltage, and ISC or short circuit current. The efficiency of the solar cell, which is eta, is equal to VMIM by VOC ISC, which is also known as the fill factor, where Vm corresponds to the maximum voltage and Im corresponds to the maximum current corresponding to the maximum power. Now let us first discuss the dark characteristics of solar cell. The junction current or Ij can be expressed as Ij is equal to Is exponential of QV by KT minus 1, where Q is the electronic charge and Is is the saturation current, which is also called as the dark current. This saturation current is obtained when large negative voltage is applied across the diode. This saturation current, Is, arises due to the diffusion of minority carriers and is given by Is is equal to Q dE N P0 by Le plus Q dH P N0 by LH, where NP0 and PN0 are the thermal equilibrium densities of electrons in the p region and holes in the n region of the junction, and Le and Lh are the diffusion lengths of electron and hole in the p region and n region respectively, and De and Dh are the diffusion constants of electrons and holes, and they can be written as dE is equal to kT by Q mu E and dH is equal to kT by Q mu H. Now the densities of electrons and holes, they are given by Np0 equal to Ni square by Na and Pn0 is equal to Ni square by Nd, where Na and Nd are the impurity concentrations in P region and N region, and Ni is the intrinsic carrier concentration. So the expression for the diffusion lengths of electrons and holes can be written as Le is equal to root of dE tau E and Lh is equal to root of dH tau H, where tau E and tau H are the lifetimes of electrons and holes as the minority carriers. After substituting the values in the Is, basically the values of Le, Np0 and De, Dh, Pn0 and Lh in the expression for Is, we can write Is is equal to A multiplied by Q dE Ni square by Le Na plus Q dH Ni square by Lh Nd, where A is the cross-sectional area of the diode. Now let us discuss about the illuminated characteristics of solar cell, which is shown by the curve B in the graph. A PN junction diode in the presence of light generates the electron-hole pairs and electric current which flows in the circuit. The expression for the electric current can be written as I is equal to Ij minus IL. So putting the value for Ij, we get I is equal to Is multiplied by exponential of QV by KT minus 1 minus IL, where IL and Ij are the light generated current and the normal diode or the junction currents respectively. So students, till now we have discussed about the characteristics of the solar cell. Now let us discuss about the solar cell output parameters. The behavior of the solar cell is characterized by three important parameters. First is the open circuit voltage VOC. Second is the short circuit current ISC. And the third is the efficiency or the fill factor, that is eta FF. We will be discussing the three parameters one by one. First, let us discuss about the open circuit voltage or VOC. VOC is defined as the voltage output from a device when the load impedance is much higher than the device impedance, that is maximum possible voltage at zero current. Hence, at I is equal to 0, V will be VOC. So the expression for VOC can be written as I is equal to Is exponential of Q VOC by KT minus 1 minus IL at I equal to 0 and then equating it to 0. So we get VOC to be equal to NKT by Q ln of ISC by Is plus 1. The second parameter which we are going to study is the short circuit current. Short circuit current, or ISC, is defined as the current output when the load impedance is much smaller than the device impedance, that is, the maximum possible current at zero voltage. So, putting the V equal to 0, I will be ISC. So, the expression for ISC can be written as I is equal to Is exponential of QV by KT minus 1 minus IL at V equal to 0. This is nothing but it is equal to ISC, which shows that your ISC is equal to IL because this exponential part becomes equal to 1, and this 1 minus 1 will result into 0. So we are left only with the IL. So ISC, ideally the short circuit current, is equal to the light generated current IL. The next parameter is the fill factor. The fill factor is defined as the ratio of the maximum output power that a photovoltaic cell can produce, or VMIM, to the theoretical or actual limit VOC ISC when both the voltage and the current are simultaneously at their maximum. So the fill factor, or eta FF, is equal to VMIM by VOC ISC. So the fill factor is a measure of how square the output characteristics are. Obviously, the fill factor is near to the unity. The higher the fill factor, the more the quality of the cell. However, for the solar cells of reasonable efficiency, it has value within the range of 0.7 to 0.85. Ideally, it is a function of the open circuit voltage only and can be calculated using the expression given by eta FF is equal to VOC minus ln of VOC plus 0.72 divided by VOC plus 1, where VOC is defined as the normalized VOC. That is, the small VOC is the normalized of capital VOC, that is, the small VOC is equal to capital VOC by NKT by Q. The above expression applies to the ideal cases only with no parasitic resistance losses and is accurate to about 1 digit in the fourth decimal places for these cases. Now let us discuss the effect of parasitic resistance. Solar cells, they have generally a parasitic series and shunt resistance, that is RS and RSH respectively, associated with them. These resistances act to reduce the fill factor, that is eta FF. Let us discuss the effect of series resistance RS. The major contribution to the series resistance RS comes from the bulk resistance of the semiconductor material, the metallic contacts, and the interconnections, carrier transport through the top diffused layer, and the contact resistance between the metallic contacts and the semiconductor. As Rs decreases, the open circuit voltage, that is VOC, is not at all affected, but the fill factor, that is eta FF, gets reduced significantly. Now this figure shows the effect of series resistance on the fill factor for a typical silicon solar cell of 2 centimeter square area, which is illuminated with 1000 watt per meter square intensity of light. It is evident from the figure that as Rs decreases, VOC is not affected, but the fill factor or the eta FF gets reduced significantly. Effect of parasitic resistance, that is shunt resistance, RSH. The shunt resistance is due to the PN junction non-idealities and defects near the junction. This results in a leakage current at the edges of the solar cell, as well as any point short circuit of the PN junction. Now it is also evident from this figure, that is, the figure is between the current versus voltage, showing the effect of shunt resistance on the fill factor of silicon solar cell. It can be seen that as the shunt resistance or RSH decreases, the fill factor and the VOC gets reduced, while the ISC remains unaffected. Here, Rs can be reduced by making the diffusion region thinner and heavily doped, and by optimizing the design of ohmic contact grid pattern. Now let us discuss about the equivalent circuit of a solar cell. A standard equivalent circuit of a solar cell is already been explained, and it is shown over here also, in which the load resistance RL has been applied, and from where and over which the output voltage has been measured. So the modified equation of the current flow will be I is equal to IL minus IS multiplied by exponential of QV minus IRS by KT minus 1. So the saturation current IS is a function of band gap and the temperature of the material. So with the increase in EG or the energy band gap and the decrease in temperature, IS and basically the IS decreases and VOC increases. Usually ISC depends on the spectrum of light and the spectral response of the photovoltaic cell, whereas the spectral response of the photovoltaic cell depends on various parameters such as optical absorption coefficient alpha, junction depth chi j, width of transition region W, surface recombination velocity S, the lifetimes and the mobilities of charge carriers, and the electric field. Now the expression for the saturation current can be written as IS is equal to A multiplied by Q dE Ni square by Le Na plus dH Ni square by IH Nd. So for the maximum value of VOC, your IS should be as small as possible. It may be seen that IS is a strong function of Ni square, which is given by Ni square is equal to Nc Nv exponential of minus Eg by kT. Therefore, the expression for the minimum value of Is in terms of the band gap can be written as Is is equal to 1.5 multiplied by 10 to the power 5 exponential of minus Eg by kT ampere per centimeter square. This indicates that as the value of Eg increases, the maximum value of VOC decreases, which is opposite to that of ISC, recommending that there is an optimum value of Eg in the semiconductor for maximum efficiency. The maximum VOC also decreases with increasing temperature. The power output decreases relative to the input of photovoltaic energy. VOC is a strong function of temperature, whereas ISC is less dependent on temperature. But VOC is less dependent on radiation intensity as shown in the figure, and ISC is linearly varying with increase in the radiation intensity. The ISC is related with the VOC for the following relation, that is ISC is equal to IS multiplied by exponential of Q VOC by KT minus 1. So after neglecting the smaller terms, the above equation can also be written as ISC is equal to A T to the power of gamma exponential minus Eg naught by KT multiplied by exponential of Q VOC by KT, where A is the area which is independent of temperature, Eg naught is the band gap at zero temperature, and gamma determines the temperature dependence of other terms determining Is, and it ranges from 1 to 4. Now, the differentiating this expression and putting Vg naught equal to Eg naught by Q and neglecting the effect of temperature on short circuit current, we can find that dVOC by dt is equal to minus Vg naught minus VOC plus gamma multiplied by KT by Q, this whole divided by T. So from this expression, it is quite clear that VOC decreases linearly with increase in temperature. Maximum voltage and maximum current. Now students, as you can see from these two graphs, which shows the variation of maximum current and maximum voltage with increase in temperature for various semiconductor materials. From these figures, it can be understood that the increase in temperature causes the percentage decrease in Vm. For silicon, VOC decreases by about 0.4% per degree Celsius rise in temperature, and the power output decreases by 0.4 to 0.5% per degree Celsius. Also, the efficiency of semiconductors with larger band gap does not affect much by temperature. For example, gallium arsenide, which have a high band gap, are less sensitive to increase in temperature as compared to silicon cells. There is one more material also, that is cadmium sulfide, whose Im does not vary at all with increase in temperature. So students, Let us summarize what we have learned in this module. By making a series of approximations, the general system of equations describing the solar cell operation can be reduced to a tractable form. This approach has allowed the ideal form of the dark and the illuminated characteristics of solar cells to be found. Under illumination, the dark current voltage curves ideally are displaced downward by the light generated current. The active region of the solar cell for collecting the latter current is the junction depletion region, and the volume of the cell materials within a minority carrier diffusion length of this region. The main parameter which is used to characterize the terminal properties of solar cell are open circuit voltage, short circuit current, and the fill factor. Thank you.